myself M. Vijay Sabareshwari, working as an assistant professor in the Department of Electronics and Communication Engineering in Sri Shanmuga College of Engineering and Technology. In this video, we are going to know about RC, RL and RLC AC circuits. So we are all know about what is AC. So AC is nothing but alternating current, that is the electrical parameters which are voltage and current both are varying with respect to time. So this is indicated by this waveform. So in this diagram, this is a voltage waveform. So the voltage is varies with respect to time. So the x-axis is time and y-axis is voltage. So the voltage value is varying with respect to time in this diagram. Voltage is varying with respect to time. So this is a sine waveform. So in general, we representing AC in a sine waveform only. So the input voltage V is equal to Vm sine 2 pi f into t. Another expression is V is equal to Vm sine omega into t. So omega is equal to 2 pi f. Here it is a frequency. Here it is mentioned as an angular frequency. So Vm is nothing but the peak applied voltage in volts. F is applied frequency in hertz and t time in seconds. So every parameter with a measuring unit is mentioned. So the positive cycle has half of the frequency and the negative has the half of the frequency. So the total duration of the one complete cycle is equal to one frequency. Then if we are adding resistance to the AC circuit, what will happen? So this is AC supply. We are seriously connecting the resistance to the circuit. So at the time of instance, the current is measured by Ohm's law. I is equal to V by R. Here V is equal to Vm sin 2 pi ft whole divided by R. So Vm by R represented as Im. So I is equal to Im sin 2 pi ft. So whereas Vm and Im are the maximum voltage and maximum current obtained in this circuit. So this is the maximum voltage. At this point, current attains its maximum value. So when resistance is connected to an AC supply, the both current and voltage are in phase. So in phase means both the voltage and the current attain the maximum value at the same time, maximum negative value at the same time, and completes its cycle at the same time. So the positive are completed at half of the frequency and the negatives are completed at half of the frequency for both voltage and currents. So that is why current and voltage are called as in phase. In or is connected to the AC supply. From this circuit we can know the some parameters VRMS and IRMS. VRMS equal to Vm divided by root 2 and IRMS equal to Im divided by root 2. So what is RMS first of all? RMS value of an alternating current is the steady state current, that is DC current, which when flowing through the given resistor for a given amount of time produces the same amount of heat as produced by the alternating current. So when flowing through the same resistance with the same time. That is, meters normally indicate RMS quantities and this is equal to the DC value. So other representations of the voltage and the current are maximum or peak value and average value. Now the next circuit, the inductance is connected to the AC supply. So the current value I is equal to minus Vm divided by 2 pi f by cos 2 pi ft, omega is equal to 2 pi f and Im is equal to minus Vm divided by omega L at t equal to 0. So the cos 0 value is equal to 1. So minus Vm divided by omega L. Finally I is equal to minus j divided by omega L into V. If you are applying omega equal to 2 pi f, V divided by 2 pi fl. So when you are adding the inductance to this AC circuit, in the complex number will be generated and J is the operator to that complex value. So inductive reactance, that is XL, is calculated by 2 pi f into L, that is omega into L. Then What is the relationship between current and voltage? So in resistance connected to the AC circuit, current and voltage have the same value, but here the current lagging with respect to voltage by 90 degree. So lagging means the voltage attains the maximum value at this point, but the current attains maximum value after the some period. So current is lagging here. After the voltage only the current attains its maximum value. So the difference between voltage and the current, the phase difference is calculated as 90 degree. So the current lag the voltage by 90 degree. So the phasor difference between voltage and the current is equal to 90. Now the next diagram, here we are connecting capacitor to the AC circuit. So V is equal to Vm sin 2 pi ft. This voltage is connected to the capacitance. The capacitor is connected in series. Now we are calculating the current and voltage. So voltage is equal to Vm sin 2 pi ft. We know that, but the current value I is equal to 2 pi f c into Vm cos 2 pi ft. So the finally the derivation is Im is equal to omega into C into Vm, whereas 2 pi Fc into V. Here I is equal to plus j omega into Cv. Here also when you are adding capacitor to the circuit, complex number will be generated and j will be the operator, but the j value is positive. Here the current leads the voltage by 90 degree. So leading means before voltage attaining its maximum value, current attains its maximum value before in the voltage. So the before means the phase difference between current and voltage is 90 degree. And the capacitive reactance is calculated by Xc equal to 1 divided by omega C. Now we are having the combination AC circuits. Combinational means with a resistor, here L, that is inductance is connected in series with a resistor. So R and L are connected in series with the supply. So the voltage R V is equal to VR plus VL. So VR is equal to I into R, but VL is equal to I into J into XL. So the total voltage V is equal to I, we are taken commonly at outside, R plus JXL, and the current value I is equal to V divided by R plus J into XL. Then impedance Z equal to R plus J omega L. So this is a polar format. In polar form, I is equal to V divided by square root of R square plus omega square plus omega square into L square, and the angle is minus pi L, because in inductance the current is lagging. So that is the notation. Minus pi L indicates the lagging current. So under the I value we are finding the determinant. So this is the only the magnitude, and the minus pi L indicates the phase value. Power factor is equal to cos pi, and the complex impedance equal to square root of R square plus omega square into L square. And this is the phasor diagram representing the voltage and current relationships. Next we are connecting capacitance and the resistor in series with the supply. Now the V is equal to Vc plus Vr, the voltage drop across capacitor and the voltage drop across the resistor. So Vr is equal to I into R, and Vc equal to I into minus jXc. And the Xc value we know that 1 divided by omega C, 1 divided by 2 pi Fc, and I is equal to V divided by R minus jXc, and impedance Z value is equal to R minus J divided by omega C. So here the plus J signifies the current leading the voltage. So in polar form, the magnitude of the current is calculated by V divided by square root of R square plus 1 divided by omega square into C square, and pi value. So positive pi means it is leading the, it indicates the current is leading the voltage. So pi value is equal to tan inverse of 1 divided by omega CR. Power factor is equal to cos pi, and this is the phasor relationship of the voltage and current. Next one is RLC in series with AC supply. So resistor, inductor and capacitor, all the three passive elements are connected in series with the AC circuit. So now the total voltage V is equal to VR plus VL plus VC. So the voltage drop across resistor, the voltage drop across inductor, the voltage drop across the capacitor. So each are calculated individually, then we are adding. So V is equal to I into R plus JXL minus JXC. XL value, XC value we know that. So finally I is equal to V divided by R plus J into omega L minus 1 divided by omega C. And the Z value we will be calculated by using square root of R square plus omega L minus omega C the whole square. So this one representing the magnitude value, and this will represent the phasor value. So pi is phase value will be calculated by tan inverse of omega L minus 1 divided by omega C divided by R, and I value will be calculated by V divided by square root of R square plus omega L minus 1 by omega C the whole square. So if it is a capacitive circuit, the current is leading. If it is an inductive circuit, the current is lagging with respect to voltage. If it is a resistive circuit, both voltage and both current, both are in phase. So in a resistive circuit, it will create the frequency that is called resonant frequency, and it is calculated by F naught is equal to 1 divided by 2 pi into square root of L into C. So at resonance, we will attain the maximum voltage of maximum value of voltage or current. So that is why the resonant frequency is important in AC circuits. So here F naught is called series resonant frequency, and F naught is calculated by 1 divided by 2 pi square root of LC. So this phenomenon is having the applications in radio tuners. So at resonant frequency, the power dissipation P is equal to V into I. So we know that V equal to Vm sin omega t, I is equal to Im sin omega t plus pi, and the P value is equal to Vm Im divided by 2 into cos pi. So this is the relationship between real power, apparent power, and the reactive power. So the real power is here, and the reactive power is here, and the reactive power is here. So the P is apparent power, and P1 is real power, and P2 is reactive power. So the hypotenuse of this triangle indicates the apparent power P, and the adjacent is real power, and opposite side is the reactive power with respect to the power factor cos theta. This is the power factor correction. We can add some other reactive power to make the reduce the losses. Thank you.